We're now recording. Let's go from current slide. Now, I don't know of many announcements that, well, I saw a few when I didn't have a place to print them, so I'll have to print those off possibly later today or tomorrow morning sometime. But there are a few things coming up that you probably do need to know about. Let me see if I can remember them all. One announcement that I was telling you about, any students interested in a 1 week summer commitment, 1 week in the summer, if you're considering a biopharma manufacturing career, they will pay you $1,000 to go and your travel expenses. So that's a pretty good deal. The deadline's sometime in January, but yesterday a student took my announcement sheet and I guess made off with it. So I don't have it back. I have no way of giving you that link. I can find it if you really need it. Okay? So I've got to find out, in fact I hope to today, whether I can get out of a faculty meeting on Thursday. Okay? We are having one on Thursday. If it's on this campus, I might be able to go to the first part of it, but then I'll have to come to the class. So I might be a few minutes late if they require me to go to the first part of the meeting. Okay? If it's on the Birmingham campus, there's probably no way I can make it at all. But anyway, I'll find that out and let you know if there's anything comes up. Like if they say, I can't miss the meeting, which I don't think they'll say. Okay? So that's Thursday. Friday, I will be out of town. I'm not going to be on the Birmingham campus or this campus at all on Friday. So if you were planning to get in touch with me Friday, get in touch with me by Thursday because I'll be leaving town Friday morning. Okay? Now, there's kind of a good news, bad news situation coming up for next Monday. Okay? The bad news is Monday's a holiday. It's Veterans Day. There will be no school. The college is closed. That's this coming Monday. The good news is that it doesn't affect us any because we meet on Tuesday and Thursday. So we won't miss any class because of that. I know you are delighted to hear that.
Holiday?
Yeah. It's Monday. Okay? And then, Tuesday, Wednesday, and maybe into Thursday of next week, if you see a bunch of people, if you see a bunch of administrators from here at the college who seem like they're on edge, and you see a bunch of other people who seem like they enjoy putting people on edge, no, that wouldn't be true. We are undergoing our once a decade, hopefully, SACS reaccreditation visit. SACS is Southern Association of Colleges and Schools, and that's our credentialing body, you might say, the certifying body. There's another name for it. I can't think what it is. Accrediting body. That's who accredits us as a legitimate community college. Okay? They will be here, I know Tuesday, probably into Wednesday, and possibly Thursday. The sooner they leave, the better it is for us because that means they have found very few things to gig us on. Now, we've been in the process of turning in paperwork for this thing for probably well over more than a year. So most of the hard work's done, but they do come and make a site visit. And if they are satisfied that everything is as we say it is, then they may be leaving earlier than, and we hope they'll be leaving earlier than they may schedule. So, if you do see other people on campus Tuesday, Wednesday, Thursday of next week, be kind to them, be nice to them. They may actually stop and ask you a question or two. But I doubt it, but it could happen. Now, I guess that's about all. Any questions on anything we've covered so far? Now, where are we and what will we be doing today? Today we're nearing the end of Chapter 3, the energy chapter. We're going to finish the chapter, and it won't take us too long, I don't think. We don't have that many more pages to go, that many more slides to go, but we will proceed with this. When we finish Chapter 3, we'll go on and get started on Chapter 4. Then at 5:45, we will have our lab, the last lab for the energy chapter, Chapter 3. And I'm sorry about this, but it's probably going to be one of the shortest lab, paper-wise anyway. One piece of paper, okay, for each of you. But you'll be doing multiple things on that piece of paper. So it's one I made up, so it's pretty short. Written-wise, but there will be a number of things to do. We will be down in 259 again, okay? So we'll be going down there. All right. Wasn't much setup for it, so I'll have to do last-minute adjustments to get that. So that means, since we'll be finishing Chapter 3 today, that means Thursday we will have class for 2 hours, and then have lab for 2 hours, the first lab in Chapter 4, and then we'll have the Chapter 3 test, the last 30 minutes. The lab, I don't think will take you a full 2 hours, and the test probably won't take you a full 30 minutes, so, but we'll allow you 2 hours for a lab and at least 30 minutes for a test. If you need more time for the test, you certainly can have it. Anyway, we'll go 3:15 to 5:15 for the class, 5:15 to 7:15 for the lab, and then up to 7:45 or later if you need it for the test. Any questions? All right, if not, where we left off last time was the energy chapter. We're in section 3.4, which is energy sources today, and we had talked about the general themes on the previous slide. Now we're going to hit the specifics. First, we'll look at petroleum. And if you remember our graphic, the petroleum was the biggest chunk of our energy pie, okay? About, in your text, 36%. So a little more than 1/3 of our energy comes from one way or another from petroleum. Now, I remember the old movies when they dug down for the wells in Texas or Oklahoma or wherever that was, and then all of a sudden here came the oil spewing out of the ground. Or the Beverly Hillbillies who shot at something and the oil came bubbling out. That was Hollywood. Okay? There were, and probably still are some, pockets of oil that will do like that. But most of that, you may have heard the phrase, low-hanging fruit, the easy-to-get stuff, it's been long depleted. Now, maybe Saudi Arabia still has that. I don't know. They seem to have a very big supply of oil. Now, the interesting thing is they're totally desert. And oil comes from living material, mostly plant. So at one time, what's now the desert of Saudi Arabia must have been a thriving rainforest, okay? Hard to imagine today, but it must have been because they have all that oil down there, okay? Most of the petroleum we're getting today is from oil-bearing rock. That's not going to spew up into the air like the old movies did. What they have to do here is drill into the rock, and some of it may have pockets of oil that could come to the surface, but then if there are pockets in there, they pump it out. And if you drive, I know into Louisiana, probably southern Mississippi, you'll see those rigs going that are pumping small quantities of probably pretty low-grade oil, but they still pump oil out like that. But most of it is they have to somehow extract the oil from the rock, okay? Now, they may be putting solvents down there or other things such as that, but the oil is from oil-bearing rock that either has oil between the layers of rock which could come out or be pumped out, or it actually has to be removed from the rock. Okay? Where did it come from? This is what I was getting at before. When it says organic, what does organic mean? Organic.
Coming from plants?
Yes, coming from living organisms. Okay? It could be plants, it could be animals. Mostly plants, though. Organic sediments. Okay? So here's what probably the story was. You probably had something like a tropical rainforest, lots of plants, lots of moisture, and the probably swampy, boggy, that kind of stuff. So when the leaves and the trees and other things fell, they didn't, the leaves that fall out here that aren't cut up with anything else, ultimately they're going to oxidize away, okay? React with oxygen, they're mostly carbohydrates, they turn into carbon dioxide and water, okay? They just sort of disappear. But if they're underwater, then they don't oxidize. So they just pile up on top of each other. That's the sediments, organic sediments. And they go deeper and deeper and deeper. Things fall over them, more and more piles on. And over time, and when they're saying time, we're talking long periods of time, okay? I'm guessing, I don't remember if the book specified, I don't see it in here, but my personal guess would be at least centuries, more likely millennia, or something in between. Hundreds to thousands of years, these things have been piling up, building on each other, getting deeper and deeper, more and more things piled onto them. This actually can occur and does occur in the bottoms of lakes, oceans, places such as that. I've got to find that there is Ethan, okay? And like I said, swampy areas like that, okay? So transform over time. How are they transformed? Initial process is probably by bacteria. Now there's multiple kinds of bacteria. Some of these are called aerobic, meaning they need oxygen to break things down. Those kinds of bacteria probably are not going to produce that much of it, but the anaerobic, those that don't require oxygen, as in underneath water, they probably wouldn't, these bacteria start breaking down those complex carbohydrates, okay? Now think about that word, carbohydrates. The carbo means carbon, okay? Hydra, hydrogen. The ATE means oxygen. So carbohydrates are a combination of various means of getting carbon combined with hydrogen, combined with oxygen. Carbohydrates. Sugars, simple sugars, fructose, glucose, any of those sugars, lactose, those are all carbohydrates. Then you get more complicated carbohydrates like starches, like you find in potatoes and breads and things like that, your grains and corn and those kinds of things. Then, over time, then you get really complex carbohydrates like wood, cellulose is a very, very complex carbohydrate, okay? And they just keep progressing. Well, these bacteria, in some way or another, pull out most of the oxygen, okay? Because, remember, they're anaerobic, but they got to have oxygen to live, so somehow they get the oxygen out of those leftover carbohydrate materials. So now they become hydrocarbons, hydrogen and carbon. That's all. No or not much oxygen left in them. So that's part of what the bacteria do. The anaerobic bacteria extract the oxygen, and leave the carbon and hydrogen, or most of it, there behind. Now, the other thing that's required is pressure, and that's why I kept emphasizing this takes a long period of time because they keep getting buried deeper and deeper, meaning more and more pressure on top. But not only that, you have greater and greater temperatures. Okay? So between the time, the bacteria, the pressure, and the temperature, and time is a long, long time, these organic sediments that were largely carbohydrates, they have other things in them, sulfur and nitrogen and other things like that mixed in with them. Again, the bacteria probably take care of most of the nitrogen because that's where they get their protein source. The sulfur hangs around though, and that's why most petroleum also has traces of sulfur in it, and that's why sulfur dioxide, if you read the literature, they call it SOx, S-O sub X, so meaning different amounts of oxygen in it. That's where those pollutants come from. Okay. But anyway, that's the original process. Now, while this is forming, you also have a lot of natural gas. Now, I don't want to say it crudely, but I probably will. If the bacteria are flatulating, they could be producing, and that's not all the way, natural gas. Okay? Natural gas is also a hydrocarbon. If basically your petroleum is the liquid form, natural gas is more of a gaseous form of your hydrocarbons. Okay? The natural gas formation is similar, except generally at higher temperatures, meaning that additional bacteria or more temperatures have basically, the natural gas has a lot less sulfur and other pollutants in it. So it's actually a purifying process, and they go from liquid to gaseous state. And the chemistry of it, I don't understand, but it has to be occurring like that. And so it would be higher temperatures and probably longer times. Okay? Now, the petroleum and natural gas often found in conjunction with one another. Let's go back to this. Oil-bearing rock. What's the process now that they're getting? What are they getting more out of oil-bearing rock than oil? The natural gas. Because it's cleaner, it burns better, more octane you might say. So it's in higher demand these days. Here's my guess. I may be wrong on this. I bet you in the old days, natural gas just escaped when they had those wells that was probably a lot of natural gas going up with the oil. They probably tried to capture the oil, no capturing the natural gas. Nowadays, they're far better, and they really want to capture as much of that natural gas because that's actually more valuable than the petroleum. Now, the supplies are limited, okay? When this slide was written, I don't know how much, if they've updated it in the text any. I don't see that they have. Okay. But when this slide was written, which was a couple of editions ago, 25% of our, we're talking about U.S., supplies are met from offshore wells. Anyone remember one of the most famous one of these? Yeah, the BP oil spill. And I didn't realize the Gulf of Mexico went down as much as a mile, but that was one of the big problems with that spill. That well was probably in excess of a mile deep. Now, at 1 mile deep, even in the Gulf of Mexico, which I always picture as a warm bathtub, because it's there near the tropics, in the tropics, and pretty warm body of water. When you get down a mile deep, it's not warm, okay? It is very close to freezing. It may actually be below freezing temperature-wise, but it hasn't turned to ice just because you have all that salt in the water, and salt keeps it from solidifying. So these offshore wells, again, the low-hanging fruit has already been gathered. They're going deeper and deeper, and that causes more and more potential problems. Because how in the world do you repair a spill 1 mile down? That's what took them literally months to figure out when they had the BP oil spill. It was just gushing oil into the Gulf of Mexico, way down there, for long periods of time at a pretty high rate of the gush. Okay, so it's pretty sad. Now, at the time this was done, it said more than 50% of our oil was imported. Now, just looking at the numbers in your book, they still are saying with over 25% of our nation's petroleum estimated to come from offshore wells that we own. Imported petroleum comes from a number of countries, with Canada leading the nations that export oil to the U.S., sending, and then they have all these various ones, and this has been changing, okay? Most remaining comes from Saudi Arabia, Mexico, Venezuela, probably not so much these days, okay? They've been having some pretty major problems. They're not exporting nearly as much. Iraq, this was probably before the, I don't know when these data were collected, but anyway, it's, we get it from several places. I doubt if we get much from Russia, but Russia is a big exporter of oil too, mostly going to Europe and the other Soviet bloc, former Soviet bloc nations. Okay, so I think now we're less than 50% imported. We've increased our offshore oil production, and we've gone far more to natural gas. So this slide was back, let's go back here, when petroleum was 40%, now we're 36%. So we've dropped our percent consumption of petroleum, and more of that from the imported was what took the hit. Now, there are some big differences here when they mention these places. Most of the oil coming from Canada, at least my understanding of it, is pretty heavy oil. It's not the nice, what they call light, sweet crude. No, there's nothing sweet about it. But it's a lot heavier and probably messier, probably has more pollutants in it. I don't know if all that's true, but I believe it is. Okay? That coming from Saudi Arabia, theirs is the light sweet crude. Okay? That's the really high quality petroleum as far as petroleum goes. Okay? Mexico, I don't know. I'm guessing maybe, I don't know. I shouldn't guess. Venezuela, don't know that either. Iraq, probably much more similar to what Saudi Arabia, because they're in sort of the same area. Okay, so that's the petroleum side of things. Coal. And again, coal at one time was the big gun. Okay, if you go back to the slide we had before, coal was following natural gas and petroleum at 21%. My guess, in the not too distant past, like a few generations ago, it was probably rivaling petroleum, and you go back a few more generations, it probably exceeded petroleum, okay? But as we saw, coal has dropped from the 21% here to 18% in your text, which probably has dropped even further, okay? And guess what? It starts the same way as petroleum. We call all these we're talking about now fossil fuels because they come from ancient times. Accumulated plant materials over, again, at least hundreds of years, more likely thousands of years. Okay? Now, processed over time. They left off the bacteria, but the bacteria are involved, the pressure and the temperature. The time is certainly involved. But coal is almost like a mineral as opposed to a liquid, and certainly not like natural gas. And as such, as I said, the petroleum, the liquid, has more contaminants than the natural gas does. Coal has more contaminants than the liquid does. So here's the progression. Now this, I'm getting a scratchy throat, so I hope it's not a cold coming on, but it feels so hot like one. But here we've got the progression. Remember, I started before talking about bogs and swamps and areas like this. This is definitely coal's origin. The petroleum probably was much deeper, as in bottoms of lakes, oceans, rivers, well, not rivers, big bodies of water, the accumulated plant material, and perhaps a lot of dead whales and things like this. I don't know what all went into it. But this is more of your surface type stuff, swamps, bogs, those kinds of things. What you have first is peat. Peat is basically just beginning to decompose plant material. Usually underwater, so it's not oxidizing, but it's being enriched in the hydrocarbons while it's using up some of the carbohydrates. It goes from peat to a preliminary like mineral called lignite, which is a precursor to coal, and then to what they call sub-bituminous coal, ultimately to bituminous coal. Now, bituminous coal is just about the best coal you can get. Still not very clean, but much cleaner than the other kind. Pure contaminants, though it still has plenty of sulfur in it to produce sulfur dioxide, which is a major source of smog and air pollution and stuff like that. Now, they've left out of the process here, and I don't know if it falls here in the sub-bituminous or where, but there's another kind of coal called anthracitic coal, anthracite, as opposed to bituminous coal. Bituminous is the cleaner, better, more BTUs involved in it. Yeah, it just works a lot better, producing less contaminants, less ash, less everything else. Anthracitic coal tends to be pretty acidic, and so it produces a lot of sulfur dioxide, which becomes sulfuric acid. Not a very clean coal at all. If I'm not mistaken, I think we have almost banned the use of anthracitic coal here in the U.S. Maybe some places can use it if they do a lot of cleaning of the smoke and the stacks and things like this to get the contaminants out. But most of what we use is bituminous coal. Now, we have in the U.S. really rich deposits of good bituminous coal, mostly out in Wyoming and those areas. Okay? Those are areas that, believe it or not, were once underwater, and the landforms have been lifted up, as you, for Physical Science 111, know, it's been lifted up by second? Yeah, plate tectonics. I'm trying to think of the word. The faulting and the folding and stuff like this, the landforms have been raising because of, like you said, plate tectonics, the pressure that is, they have nowhere to go up. Okay? So then some of that very old stuff that used to be under an ocean bed is now, up in rocks. Okay? Really high for an ocean bed. If you think about Where is Salt Lake City?
Utah.
Utah. Okay. Well, where basically is Utah?
Kind of west central.
Okay. Good description of West Central. West is California, and you come in from California, which is pretty wide, not a super wide state, pretty wide state. And second,
You got Nevada.
yeah, and you still got Nevada, and then Utah. So it's about at least 3 states, maybe 4 states in from the Pacific coast. And yet Salt Lake was probably at one time maybe part of the Pacific Ocean. So there's been a lot of uplift in that area. You got the whole Rocky Mountains in there, okay? So we're talking long, long periods of time for all that to have occurred. Okay? Now, let's go back to the anthracite coal. Most of the coal mined in our area, I think, is anthracite coal. But we're still mining it. What are we doing with it?
Money, sell it.
Yeah, shipping it to South America and other third world countries that live on different planets, so it doesn't mess with our area, right? Okay. They don't have the environmental regulations and protections that we do. So they are burning our cheap coal because it's still cost effective to do that to some extent. But, here's diamond. Good. Okay. So, that's probably enough of this. Coal, believe it, no matter what the politicians say, coal is on its way out. And it's not because of politics. Coal is on its way out because natural gas they're finding fewer and better ways to get it, much cleaner, much easier to get, the coal, again, the low-hanging fruit, that's been mined already. They're having to go deeper, more expensive to mine, and it's getting messier and messier, okay? So it's on its way out. And they were told that. The reality is it's on its way out, and yet they don't want to believe it, okay? And as someone said, they believe the guy said, I'm going to save your jobs, and the plants are closing faster than they ever have before. So that's another story. Here's the problem with coal. One of many problems with coal. As I've said several times, it contains far more impurities than petroleum, certainly than natural gas, and just about anything else. It's a rock. I said that. It's a mineral, or very close to one. So there's other stuff in it, as in other minerals. Now these minerals don't burn. When you burn the coal, the carbon burns around them and leaves this. They go up in smoke, literally, okay? They go up in the stack and they form the ash, okay? Now, because it comes from the ground, and even the purest coal is going to have some other minerals in it, and the not so pure coal will have even more of them. When they burn like that, the other minerals actually probably liquefy or even vaporize. But then when they cool, the smokes and the ash cools, then they form little particles, usually spherical particles, called spheroids. They're like spheres. And I'm not certain on this, but it's my guess. If any of you driven out of Birmingham, it's before you get to U.S. Steel and those places, but it's along there, getting close to Inslee and Fairfield, somewhere in there. But it's just sort of right out of Birmingham, okay? And maybe about Arkadelphia Road or somewhere there, and you see a big, big mound over there to the right. Huh?
To the left if you get out of the city.
It's what?
If you leave it going north, it's to the left.
To the left, yeah.
Right, southern,
yeah. And what is that? Do you know what that mound is? I believe the name for it is slag. That's left over. mostly spherical trash, materials left over from all the coal burning and maybe some of the impurities from mining and purifying the iron ore and other things too. But it's a whole bunch of that, and there's a whole mountain of it there. And I'm not sure they can do much of anything with it. It's not good for growing things. It just is a pile there, okay? So, it's good it's not in the air, but probably it was in the air at some point. As I said, all these that I've mentioned, even natural gas to some extent, but mostly coal, has lots of sulfur in it. Now, why sulfur? Carbohydrates make most of our bodies and plants and everything else. But our muscles and stuff are made of proteins. Now, proteins are mostly carbohydrate too. I mean, if you look at a food thing, you'll see that you burn about as much protein as you do carbohydrate. You get about the same heat out of it. The difference, though, in proteins, they have nitrogen. And usually with nitrogen, to some lesser extent, they have sulfur. Your proteins are usually quite high in sulfur. If you think of one of the best sources of protein, a good source of protein would be an egg, right? And have you ever wondered what makes the yolk of an egg yellow? Mostly sulfur. That's why that rotten egg smell, that's hydrogen sulfide. The bacteria have been eating away and leaving hydrogen sulfide. That's exactly that smell. Sulfur, when it oxidizes, like when you burn coal, that's lots of oxygen there. The sulfur oxidizes and becomes sulfur dioxide. SO2, a lot like CO2. Sulfur dioxide, as opposed to carbon dioxide. That's a pollutant. But then you take, let me get my pen set up. Sulfur dioxide and combine it, it gets into the air, of course. And then when you have rain, that's H2O. What does that yield? H2SO3. I can't remember for certain, but I'm pretty sure that's sulfuric acid, which is one of the strongest acids we have. So this produces then acid rain. You also have nitrogen that's either in that organic matter, but more likely from the air. And when you have nitrogen combining with oxygen, and probably a 2-to-1 ratio here, you get 2N2O. That's probably not the one I want. Let's just combine one. You get NO. You probably want NO2. I don't know the exact. You might have 2 of these. That would be it. And that gives you 2NO2. Okay? You take NO2. Nitrogen has lots of different oxides. Combine that with water from the air, and nitrogen's all over in the air. I botched this up. I think it was N2O2. Whatever. You combine those together, ultimately you get HNO3. What's that? Nitric acid. Another one of your strongest acids out there. Okay? So have you ever heard of acid rain? Well, all rain is slightly acidic. But if you have lots of industrial plants that are using lots of coal, producing things like steel and things like this, they are pouring sulfur oxides and nitrogen oxides into the air. Later when it rains, they will combine and form some pretty strong acids. And those acids have actually led to deforestation. Okay? other words, living, growing, beautiful plants, trees, and stuff. With acid rain, the leaves die. And there were huge blocks of, the Soviet bloc countries, Russia, East Germany, and several of the others. I mean, the Soviets were pumping up industrial production. Never mind what it's doing to the atmosphere. Well, that air from there blew into Europe in huge areas of beautiful, maybe not virgin forest, but beautiful forest land just started dying. We had some of that up in Ohio, down from Pennsylvania, where they have, they call Pittsburgh the Birmingham of the North, don't they, or something like that. But anyway, where lots of coal is found, lots of industry. That air from that swept down into the Ohio Valley, killed lots of trees. Lake Erie at one time was so polluted, there were hardly any fish living in it. They have cleaned it up. That's one reason that EPA was founded, Environmental Protection Agency, the air and the water. Between those two, we were doing a really poor job. They've really cleaned things up. The Clean Air Act, Clean Water Act. Now I think you can actually eat fish out of Lake Erie. There were a while, there weren't any fish, and then for a long time before and after that, you wouldn't dare eat the fish because they were so contaminated with mercury and other things. Now they've got it cleaned up so much, I think you can now eat fish that come out of Lake Erie and some of the other ways. Okay, but that's where your acid rain comes from. Sulfur leads to sulfur dioxide, which is a pollutant, which also causes acid rain. Now, as I said before, these three, petroleum, natural gas, and coal, that's what we call our fossil fuels. And if you go back a few slides ago, petroleum, natural gas, and coal, that accounted for 40 and 44, 84% of our energy uses were from fossil fuels. In your text now, it's 18, 27, and 36. 36 and 27 is 63 plus 18. That's 81. 81% down from 84%. Not that much of a change, okay, but still a change. In the right direction, but still got a long ways to go. Those are our fossil fuels. Now, a very clean energy source, a renewable energy source, natural energy source is moving water. It's renewable with rainfall, and fortunately the rains do fall. Okay, rains fall at upper elevation and the water flows downhill. Okay, the gravitational potential energy when it's up there converts to electrical energy, but it gets piled up behind the dam, and that gravitational potential energy becomes kinetic energy as it turns the turbines, and those make the electrical energy. Okay? Hydroelectric plants, though, only generate about 3% of the U.S. total energy consumption. Well, why don't we build more of them? If they're clean, if they're renewable, all these good things, why don't we build more hydroelectric plants? Well, again, in sort of a different way, we've already harvested the low-hanging fruit. In other words, most of the rivers that have enough fall in them, and I don't know if y'all are familiar with geography enough to know there's a thing called the fall line, okay, that pretty much goes, I think, through Montgomery, Columbus, Georgia, Macon, Georgia, Augusta, Georgia, and it goes west also. Above that, you have pretty good drop-off in land. Below that, you're in what they call the coastal plain. Okay? In the coastal plain, you can't build dams high enough to convert this, and if you do, you're covering huge acres of good tillable farmland, cities, other things like this. No one would put up with that. So you have to be above the following, okay? But if you think about just the state of Alabama, now let me get my map back here. Let's go to, well, this is probably not bad here, okay? I'm not familiar so much with northwestern Alabama. Any of you familiar with the areas like Florence and those areas? That's 16, 17. What's that?
I know there is a dam in Florence.
I can't hear you.
I know there is a dam in Florence.
Yeah, there's got to be. I want to see if it's listed on here. Wilson Dam. Okay? That's on the Tennessee River. And that backs up water because you have good fall, you know, and stuff like that. So there's Wilson Dam. There may be others. Wheeler Dam. Okay? Wilson Dam.
Martin Dam.
Second.
Martin Dam.
Martin, Lake Martin? Okay, that's down further, closer to where we are. Oh, yeah. Lake Gunnersville. I don't know what the dam is named, but that's it. Here's one here. I don't see the dam, but you know there's got to be a dam somewhere here to back up the water there. Just look at most of these. Anywhere you see, Tennessee River is a wide river, but you see it's got dams that are backing it up. There's got to be one in here. I just don't see the name of it. There's one right here. Here's the Little Bear Creek Reservoir. They don't name the dam. This one, I don't know what the name. This is Cedar Creek Reservoir. That's got a dam on it. You just go, all these. There's one over here. Flip the page. Here's in Decatur. Tennessee River is big and wide, so look, I think if you look hard enough, you can find several dams on this. I just don't see any now. There's got to be one here. Because you see, this is all backed up there. That's in Huntsville. It's probably not a huge one. There's Gunnersville Lake, and there's Gunnersville Dam right there. Someone mentioned that. Okay? Huge hydroelectric plant. Okay? Here's Scottsboro. Again, Tennessee River going through it.
So you go up right on the Tennessee line, you got Nicky Jack now.
Is what the name of it?
Nicky Jack. That's the Tennessee line. Yeah, it's on the other side of the Tennessee line right over.
I see it. I see Nicky Jack Lake, so I bet you the dam is just up from there. Yeah, so that's right there. Just all over in these northern counties, you have these hydroelectric dams. Here's
Leesburg, you go in Cherokee County, they got a dam up there.
absolutely. Now we probably produce way more than 3% of our energy. Alabama energy comes from hydroelectric. But picture this: these high population states in the Northeast. Do you think that people can afford to lose big acreages of land up there? No, the land is way too valuable. Too many people living there. They have to displace too many. They built these dams back when we were pretty sparsely populated, especially up there. And therefore, they could just come in and take over the land. They probably paid maybe not a super fair price, but a decent price. And the land was cheap. And people could be bought out, you know. But you go through all these northern counties and you see all these lakes. There's Bear Creek. I wonder if that's the name of the dam. Over here is another one. I just don't know the name of that one. But they're all over the place. There's Gunnersville Lake again. There's the dam right up there. Over here, yeah, this has to be Smith Lake. Yeah, there's Lewis Smith Dam right down here. That is a bigger lake. You know, no huge body of water, but it gets backed up all over the place. Big hydroelectric dam there. Lake George here, they don't name the dam. I bet you that's got a dam. That's near Coleman. Another one over here. They're just all over the place here. We have, here's the key, the growth potential is limited by decreasing availability of new sites. We've garnered the low-hanging fruit. The places that were easy to build dams, cheap to build dams, relatively cheap, they have been taken. And now, guess what? All around those lakes we just mentioned, people have lake houses, okay? And those are pretty expensive lake houses, some of them. And they don't want the lakes going down. So they don't want you generating too much hydroelectric energy, especially in a droughty time when the water is being used up. If they lower the lakes too much, boy, those landowners just start screaming bloody murder. You know, that we want our lake. We pay big bucks for these houses. You know, we want the lake. So they're limited. So that's why we're probably never going to get more than 3%. There's just not that many more sites available. Nowhere in the southern part of the state you can do anything such as that. Okay? Because in the coastal plain, if you build a dam, you're going to flood tons of acres. Not like Smith Lake, which is just all over the place. That's really, really deep because the land is really dissected. Down there, the land is really flat. You build a dam, you flood everything behind it, and you don't get very much drop. So you have to be above the fall line. All right. So moving water, excellent source of hydroelectric power, very limited availability. Nuclear. Now, we've talked about this several times based on the nuclear fission reactions of uranium and plutonium. Now, I don't know if y'all are familiar with uranium and plutonium. I think in your book somewhere, probably chapter 8, you can find the periodic table. If you find uranium on it, you have to go way down here at the bottom, and there it is, number 92 out of 103. So it's way near the largest atom out there, okay? Plutonium is 2 over at 94, okay? Huge atoms. These atoms are somewhat unstable, meaning you hit them with a few neutrons and they start splitting. When they split, they give off enormous amounts of energy. E equal mc squared. We talked about that before. Incredible amounts of energy. That's what nuclear fission is. The splitting of big atoms into smaller atoms. And that releases, remember, those weak nuclear forces and strong nuclear forces, which were so much stronger than anything else. That's the energy coming out of those. Okay? What's the problems with it? Say again? Safety, for sure. And I don't know if we touched on this one before. What's the waste product of nuclear power plants? Highly radioactive materials that really can't be used for much of anything else that we know of now. What do you do with all this nuclear waste?
Put it in water.
Aha, good idea, huh? Actually, for the longest time, we were shipping it to somewhere out there in Utah, I believe it was, a mountain, either named Green Mountain or White Mountain or some sort of color mountain like that, because it had some natural caves somewhere way deep inside of it. They got into those caves, they filled and sealed stainless steel, heavy duty containers that they hoped were going to last. Hoped were going to last. Because nuclear materials like this, they measure them by what they call half-lives. Okay? For instance, radon gas has a relatively short half-life, about 4 days. Okay? Within about 4 days, about half of your radon gas will decompose into something else because it's radioactive. It's a nuclear reaction. The byproducts here have lives in the thousands to 10,000s of years. So that means we've got to store that waste for way longer than we have any idea those containers are going to be able to contain it. And it's in the bottom of a mountain somewhere there in sparsely populated Utah. And what will be the dead giveaway is when White Mountain starts floating red. No, Green Mountain, or whatever the name of it is. Now, I think they quit storing there. They refused. And I remember, this was really scary to me. We had just moved to the Birmingham area, which was back in '86. And it was within a year or two of that, we heard the story of this train that was on its way down to good old Greene County, Alabama. Okay, what's in Greene County, Alabama? Anyone know? Well, there's Green Track. Okay, I think this was even before Green Track, but most of the other, it's a very poor county. And most, I don't know, this is a gross exaggeration, but a lot of Greene County is used as landfill. Okay, because it's a very poor county, and they will do just about anything for revenue. So they will do landfills there, okay? Well, this train was coming from the northeast, making its way through. I don't know if it quite got to Birmingham or not, but someone was alert enough to realize what they were doing, and they had a court injunction and stopped it. I think they sent it back because that train had nuclear waste from nuclear power plants up in the northeast on its way to bury them in landfills in Greene County, Alabama. Now, if you think about Greene County, Alabama, does anyone know one of the seats, like the county seat of Greene County? Anyone know that? It may be Utah. Is that right? Somewhere in there. But look at what is south of this region here. I know when you go through Tuscaloosa, you go into Greene County somewhere there. I think Utah may be the county seat. I don't know for sure, but something like that. There's a river, there's a river, there's a river, there's a river that's run off here, and it goes down into Mobile Bay. And a lot of people live downstream. Not that many live up here, but a lot live downstream. And guess where water flows? Downhill. That nuclear waste, if it hadn't been properly contained, which the odds are, it had dumped it and got out of Dodge and buried it. Who knows where it could have gotten to? Who knows how many millennia it would have taken for that to keep polluting southern Alabama, Mobile Bay. I'm glad someone caught it. That train, I think, was stopped before it got to Birmingham and sent back where it came from. Okay. So that's some of the problems with nuclear. Okay. Safety, but also byproducts. Now, what happens? How does nuclear power work? Well, you have these fission reactions which are producing enormous amounts of energy. The water is heated in those reactors and then used to produce steam. I mean superheated steam to turn the generating turbines and produce electricity. It's a very productive means of producing electricity. This is the same process that petroleum, natural gas uses. They just burn those, produce heat the water, produce steam, and turn the turbines. That part is the same no matter what's producing the heat. It's just now you've got nuclear reaction doing it. No fossil fuels, no sulfur dioxide, none of that kind of stuff. But you also have waste products that you don't know what to do with for millennia. Okay, it's amazing. Now, here's the other thing. There is so much heat produced in these nuclear power plants. There is in every plant, but the nuclear power plants, there's so much. They cool the towers, they cool the rods, they have to cool everything. That heats up the water. Now, just like the hydroelectric dams are on water, so are nuclear power plants, because they need huge supplies of water, mostly to keep things cool. But if they heat that water and then send it downstream, you just change the ecology downstream. Now everything's gotten hotter. Your plant, your animal life changes. You can, y'all don't remember, I don't think, the advertisement that said, you don't mess with Mother Nature. You know, I don't know if any of you remember that. We've been messing with Mother Nature a lot, and usually it doesn't turn out well. Okay? So, like Amanda said, safety. That is a big issue. Waste product, what you do with the heat. What they do, they build these huge cooling towers, and they send the heat up into the atmosphere. When they get the water cool enough, then they release it and send it downstream. But they're always doing that. It's quite a process. Over in Burke County, Georgia, where I grew up, not born there, but grew up there, went to high school and stuff. They're on the Savannah River, and they have one of the biggest nuclear power plants, not maybe the biggest, but one in the, and that's the Vogel Power Plant. And they've just opened the U.S. reactor, first reactor that's been opened since 3 Mile Island, I think. So we've gotten sort of back in the business of nuclear power production, and it's pretty clean electricity, you know, cleaner than fossil fuels and that kind of stuff, but there are all sorts of hidden issues with it. All right, so what do we do from here? That's what we've been doing in the past, and notice that nuclear had gone from, let's go back to here. When this slide was produced, nuclear was 8%. It's still sitting at 8% on this book. It may start increasing slightly, but this, a lot of obstacles to overcome there, so I'm guessing it's probably not going to do that much more, okay? So, what do we do for tomorrow? That's what we've been doing today. Now, I also want you to just think about this. If our fossil fuels, petroleum, natural gas, and coal, if they are using this plant material that has been stacked up and piled up and built up for millennia, and we're using it now as fast as we can get it out of the ground, okay? The sooner we discover it, the sooner we pump it, the sooner we sell it, the sooner we burn it. And we're doing this in the span of just a few lifetimes. Since the Industrial Revolution started, what was that, back around late 1800s? And now we're just barely into the 2000s, 200 years. We have been burning this stuff as fast as we can find it. But it took millennia for it to build up. Hey, there's going to be some point, and it may not be that far away, that we can say, hey, you know, we don't have this unlimited resource. We've used most of it, again, the low-hanging fruit, the easy-to-get stuff. We're going to have to go deeper. We're going to have to drill more. We're going to have to find new techniques to get it out. And at some point, we've expended most of what's easy to get. We better be thinking about tomorrow, okay? What energy sources do we need to use? There are alternative sources of energy, ones that are different from those commonly used today. Now already we're into this, okay? From when the book was written, in fact, you saw on the cover, the first thing was all the wind farms. We've already started that. The book caught that, okay? Today, fossil fuels, coal, petroleum, and natural gas, then nuclear and falling water, okay? That's mostly what we're using today. We're down to, what was it, 3% here, 8% here, most of it here. This is unsustainable, completely unsustainable. Maybe for a few generations, but after that, it can't work anymore, okay? It won't work anymore. So what do we do about tomorrow? Well, we have good old sun up there. Sol, sun, that's where all this came from. Fossil fuels, coal, petroleum, natural gas, those little green leaves out there were making the chemical change, using the energy from the sun, storing in chemical energy. Then the bacteria and all the other things got involved with it and converted it to fuels we could use. Now, nuclear didn't come from the sun. Of course, nuclear is what's producing the energy on the sun, but that's fusion reaction, not fission. So that's a different issue. The falling water, that came from the sun. Because what heats the water off the oceans? The sun. Gets it up into the clouds, it moves, falls over land, runs downhill, and we catch that energy back. Okay? That came from the sun. So all these except nuclear, 8%, came from the sun. Well, why don't we get it directly from the sun? Why don't we become like those little green leaves and capture that? And that's what solar cells and other things like that are doing more and more. You have a calculator on your desk there? What's that little strip at the top?
I think it's the charger.
It's what?
I think it's like how it gets power.
Yes, and how does it get power? Light. That won't produce electricity in the dark, only in light. And you have it out in the light, it's going to be, so there we have solar energy. Not from the sun necessarily, but light that ultimately came from the sun. So we're already doing more and more of this. Now, what I don't understand, have y'all seen these great big areas where they run these ultra high frequency power lines that go from the generating stations to wherever they're carrying it to? They have these cut across the state, and they keep it pretty much cleared out underneath them. Big steel towers, lots of wires up there. No trees around. They've cut them all down. Why don't they have solar cells every place they can have there, capturing the sun and adding to the grid? Right there, there's the power lines, there's the sun. Why aren't we doing that? Well, because the power companies are in cahoots with the petroleum companies, and they don't want to promote. I'm sorry, should I say this? Maybe not. Okay, but there we have this place. Why aren't we using it? Okay. Geothermal. What does that mean? Heat from the earth. Thermal means heat. Geo means earth. Heat from the earth. What in the world is heat from the earth? Those who are in 111. What was that about Iceland?
Hot springs.
Yes.
Or like the Yellowstone geysers and stuff.
Yes, exactly. And those, Iceland especially, is way up north. Really, really, really cold area. Okay? You think they have big fuel bills? Did it say so? Well, guess what they do? They're a volcanic island. Okay? So what they do is they drill down into the volcano, not into the actual active volcano, but into the volcanic rock, getting close to where the heat from the volcano is, pump water down there, it turns to steam. No fossil fuels, no nuclear energy, no nothing, just a hot rock, changes to steam, pump it back out, pump it under the roads, into people's houses. They heat everybody's house, basically for free. Just the cost of pumping the hot water. And they're very, very cold. Everybody is nice and toasty inside because geothermal. Trouble is, do we have any geysers around here? No. Do we have any volcanoes around here? I hope not. Okay. Yeah. Not every place is accessible to that. But boy, we ought to be using it like crazy where we have it. Why do they have hydrogen gas here? What is hydrogen gas? It is the lightest gas that there is, the lightest element that there is. It's number one on the periodic table. Right up here, hydrogen. Uranium was down here at number 92, plutonium 94, hydrogen number 1. One proton, generally no neutrons, one electron. Simplest atom there is. But in that simplicity, it's one of the most reactive atoms there are. You don't find much pure hydrogen around, okay? The sun has a lot, but we don't have much because hydrogen is combined with everything else. Carbohydrates, hydrocarbons, just about everything has hydrogen in it. Hydrogen reacts with everything, okay? Now, another substance that reacts pretty freely is over here at number 8, and that's oxygen. Oxygen is one of the most reactive gases also, and it is required for combustion to occur. That's to burn wood, to burn coal, to burn fuel, to burn natural gas, to burn anything, you require hydrogen, okay? That's what your injectors in your cars are doing. Everything requires oxygen to burn, right? Now, hydrogen is a very reactive gas. Does it burn? Does the name Hindenburg mean anything to anybody? Say again?
It's a hydrogen blimp. Was a hydrogen
Yes, it was a hydrogen blimp. And what happened to that hydrogen blimp? Yeah, it exploded. They don't know exactly why, either lightning or friction or something, but it was the lightest gas, so it made the best blimps until something happened, and then when it exploded like crazy. So hydrogen gas will burn like you wouldn't believe. Now, what are the byproducts? When hydrogen oxidizes and burns, what's the leftover? Whoa, where did that go? Okay, like we talked about here, what is the impurities? What is the leftover when oxygen burns? It's called hydrogen oxide. Does anyone know what that is? H2O. Water! Can you get much cleaner of a byproduct than that? So if we can burn hydrogen gas, boy, our waste product is water. Not very dirty waste product, is it? In fact, it's pretty clean. The trouble is getting hydrogen gas. Because to get it, you have to extract the hydrogen from something else. And that process of extracting hydrogen takes almost as much energy as you get when you burn it. Okay? So it's sort of a dead end. Now, there were some folks over in the automotive program a few years ago that were trying to use the burning of hydrogen to supplement combustion and what was that called? Was it renewable fuels or something like this? There was a project over there.
They're probably renewable fuels.
Yeah. And so what they were doing, I think, was using excess electricity from the battery generating type thing to, what is the name? Electrolyze water that separated the hydrogen from the oxygen, and then get the hydrogen and burn it, inject that into the fuel mix, and that burned really well. The trouble is it took as much energy to get hydrolyze the water as you were getting out of that, so it was a net, not much gain, maybe even a loss. So I think they had to give up on it, but it was a good effort, a good concept. Just didn't work, okay? Now, fusion. I mentioned that a little earlier. Where does fusion occur? The sun. That is the ultimate nuclear reaction. Fission was the one where you split the big elements, okay? Fusion is the one where you fuse or force together small elements, as in hydrogen fusing to helium. Number one fusing to become number two, okay? That produces way more energy the fission did, the nuclear. And the byproduct is helium, which is an inert gas, and it's not going to contaminate anything. The trouble is, sort of like it was with hydrogen gas, it takes more energy to produce a fusion, or so much energy to produce a fusion reaction that the net that you get out of it is not that great. And they're really hard to control. And hydrogen gas, and this is another problem here too, hydrogen gas is such a light gas, it's hard to contain it because it just floats through anything. If you have rubber tubing, it just makes its way through the rubber. So the only way to store it reasonably, because it's so light, you don't want your equipment floating away, you pressurize it. When you pressurize it, it's more easily to escape because it's under high pressure. So maybe you liquefy it, but then it takes so much energy to liquefy it that you've lost the benefit of burning it. Okay, so and that's true for fusion too. It's hydrogen gas you're going to be fusing. So there are problems, but these are areas where we need to be looking and trying. And the current efforts are a concept they call cold fusion, fusion that occurs at much lower temperatures. I'm not sure they've ever achieved it. Frankly, I'm not sure they can achieve it, but they're trying. They are really trying. So let's look at some of those, the solar technologies. Okay? Now, the ones like in your calculators, like that you have on the solar panels in your houses, if anyone has any of those, these are solar cells. They directly convert light into electricity. Now, one sort of negative part of that is that becomes, what does your calculator use? What kind of electricity? DC, direct current. That's what solar cells produce. And that's the problem with my idea of why don't they have solar panels in these stretches of power lines? Well, the power lines are AC, the solar cells are DC. So you'd have to have conversion going on all along that, and that probably would be a big pain in the neck or some other body part. Okay, so that's it. The solar cells can do a lot. What uses direct current? What are some things that use direct current? We mentioned your calculators. Cars, yeah. The only place that alternating current is in your generator that's producing, and it's immediately changed to DC, right? With your dual diode converters or whatever, that changes it back to DC. Your cars, computers, anything that you have that between the plug in the wall and the device, you have to have some sort of thing. It doesn't have to be this big and ugly, but that is converting AC coming in to DC going out, going to the computer. Okay? Think of your cell phones. There's always a box of some nature on the plug. If there's a box, that's converting. So everything like that has that converter on it, doesn't have to be big and ugly like that, those are DC. So we should be doing just about everything we can on DC. Now, you can convert DC to AC, but again, you lose some energy, there's things involved with it, but we can do it. Now, the thing they call a power tower, it doesn't have to be a tower, it can be a tower laying down, but mirrors focusing sunlight to heat water for steam generation. Okay? It says a lot, doesn't it? When I was at Georgia Tech in grad school, unfortunately I lived in the new dorms, which were way on one side of campus. All the classes were here, but I walked across this sort of open area, and in the open area was this big, long, trough-looking thing, and what it was mirrors. And these mirrors were parabolic, meaning they focused on one point. And in the middle of that point was a huge pipe there, dark-colored pipe that had water or some other liquid flowing in it. And these mirrors focused the energy. They were facing, so they caught most of the sun most of the time, and they focused that onto the water, getting that water very hot, produce steam. They were trying to do that. Well, power towers, they do it, and towers as well, focusing sunlight to heat the water to produce the steam, and then the steam is used to generate electricity. Here it's using sunlight rather than fossil fuels, nuclear energy, or something else like this. Clean. Passive applications. Designs to use solar energy flow naturally. Now, I kind of drive my wife crazy, I think. Well, I know I do, okay? But one thing I do every morning, now that we're using heat, I go around to the rooms that have blinds in them, okay? Except the bedroom, she doesn't like the blinds open in there, so I don't do her that. So, but the other bedrooms and stuff, I open them up in the morning to catch as much heat as I can during the day, as much light to come through the glass, warm up, become infrared, to heat the room as much as I can passively, and at night close it up so it sort of adds another layer to keep it from being lost to the outside. Okay, that's just my stingy little way of doing everything. Now in the summertime, I open the blind so it deflects the sun back outside, so it doesn't, the direct sunlight doesn't come in. Again, driving her crazy. Okay. But that's sort of the fun of it. Okay? Passive application. My father had a first cousin, older than he was, who married an architect. And this architect, I think, had graduated from Duke University, pretty sharp guy, I think. And he, way back then, I mean, we're talking the 1940s, 50s and stuff, he was designing his houses so that the slant of the roof, he always had them facing south, the slant of the roof was the latitude where the house was located. And then it had a long overhang in this direction. And he made them look good, okay? And what it did, in the summertime, when the sun was above that, the long overhang shadowed, it kept the sunlight from coming in. In the wintertime, when the sun was below that angle, then it was heating the windows. He had lots of windows inside here. Passive solar energy, okay? Using that energy flow naturally. In your text, now, I haven't been keeping up with turning the pages. At the top of page 77, it said, grow your own fuel, biodiesel. I should have mentioned that earlier. That sounds like a fossil fuel, and it is, but what do we mean by biodiesel as opposed to regular diesel?
It has like animal fats and vegetable oils.
Say that again?
It has like animal fats and vegetable oils in it.
Absolutely. From recently grown plants. Not fossil fuels. They haven't collected all those sulfurs and things like that. It's just pure, like you said, vegetable oil. Brazil was trying to do this, and I think they have been fairly successful. They have committed themselves to growing more soybeans and more corn, not to feed their nation, but they do, but also to manufacture. Because guess what? Brazil doesn't have oil supplies. They were having to import all their oil. So what they did, they committed themselves to growing more oil-producing plants, not to use for cooking oil and stuff like this, but to use as diesel. Or take it another step, refine it just like you refine oil and make petroleum, gasoline. Take the oil from that and produce ethanol. And we, today, most of our service stations mix and have about 10% ethanol, don't we?
10% is what our EPA allows.
What's that?
Our EPA allows 10% maximum. Then you got E85, which is 85%, and ethanol,
Right, so that has 15% alcohol, right? And problem with that. It's a good idea, and we have cut down our imported oil because we have a lot of grains and soybeans and other things. We can produce that. What's the problem with it? We are taking away from food and driving up food prices. Because not only are the grains and the soybeans eaten by people, they're also eaten by our livestock. The pigs, the chickens, and the cows are eating lots of grain. And so when you divert the grain for fuel, it raises the price for that. That raises the price for meats. And we love our meats, don't we? Okay? So there are some costs that way. But there's another thing. Any of you ever operate small engine stuff like lawnmowers and what's the problem with high ethanol content using?
We don't want to stay.
What's that?
We can't keep it in a gas tank and not use it up.
Right.
It ends up. It's very corrosive.
It corrodes the plastics and the other things because the alcohol is a little more corrosive than the gasolines and stuff are. So there are problems with it, but it's a good idea. So it's a grow your own fuel. That's exactly what Brazil's doing. But then the sad news on that is Brazil is cutting down rainforests to plant more soybeans and corn so they can produce more fuel, but they're destroying the source of most of our oxygen, and a lot of our plants and a lot of our animals. So there are big costs in that too. The person behind the science that's mentioned in this chapter, we've used his name, hopefully not in vain, is James Prescott Joule. He was a pretty interesting character. I don't want to take too much away from this, but he was, the way the book phrases it, he was a delicate child. Now, his father was fairly wealthy. Not because he was landed gentry, he was anything but the father was a brewer. He made beer, so he made a good living, a very good living. This was about the time the Industrial Revolution was coming into fruition, and so he had plenty of bucks, and his child, James Prescott Joule, was very delicate, they say. We think what that meant was he was slightly hemophilic. He was a free bleeder. If he got a cut, he didn't have enough platelets to stop it. So he couldn't work in the brewery. He couldn't do things, but he was a brilliant kid. And so he hired tutors, brought them in, and Joule did some of the most incredible experiments for his day and age that were done. He was taken under the wing of this really high-powered physicist at the time, probably one of the top. His name was William Thomson. Now, why he was such a high-powered guy, he was landed gentry. He was Lord Kelvin. That's where the Kelvin temperature scale comes from him. He put together we'll talk about him in the next chapter, most of the laws of thermodynamics he came up with. He recognized Joule's work and how important it was. He brought him into the Royal Society, which had been open only to the upper crust, because they were the ones mostly educated. They were the ones allowed to go to university, the ones who had the money. Well, Joule, his father had money, but that was brewery money, that was dirty money, sort of, it was still money and still spent. But he was tutored, and he was brought into the Royal Society as a full-fledged member. On the first commoner brought in, that was back when class was really such a big deal. Fortunately, hopefully we're getting away from that. Okay, anyway, let's go on. Myths, mistakes, and misunderstanding, bottom of page 79. Recycle or reuse, okay? Is it a mistake to say you're recycling plastic bags if you take them back to the store where you shop? No, you're probably just reusing the plastic bags. Now, what's the problem with the plastic bags anyway? There's multiple problems. plastics come from? Just about all plastics come from. The plastic in these glasses, okay? All plastics. Where does it come from? Petroleum, exactly, okay? So there we're using petroleum products, okay? Now, the problem with plastic bags, and most other plastics too, when they finally get around to decaying away, they don't completely decay. And most of them wind back up, unfortunately, in the ocean. And there are huge areas of the ocean that are almost dead spots now. And part of the reason is plastics, they wind up being about the same size as plankton and other things at the bottom of the food chain in the ocean. And the fish come along thinking they're eating plankton and they're eating plastic that they can get absolutely no nutritional value from, and they're starving to death. And when the bottom of the food chain starves, everything up the food chain starves. And so there are huge areas of the oceans that are actually dying because, maybe for other reasons too, but largely plastics. And we are using plastics like crazy, and we need to stop, okay? And I get so mad at myself every time I go into the grocery store, forgetting to take in the bag that's in the back of my car, and they say, you want plastic? I said, oh yeah, I have to. I just left my bag in the car. So I'm getting better at it, but I'm still got a long way to go. You've got to stop using. And I hardly ever, sorry about this, drink water from a bottle anymore, okay? Unless I'm refilling it and refilling it and refilling it, because every one of those bottles is going to wind up in a landfill somewhere, and it's not biodegradable. It's to some extent photodegradable, which means light will break it down over a long period of time.
Is that what your Walmart sacks from like 10 years ago? Is that what they did? That's when they just like fall apart?
Yeah, in time they'll fall apart. Yeah, and if you have them out in the sun for a long time, you go to pick them up, they just sort of fall apart. But those little bitty particles that are left, they stay little bitty particles, and nothing can use those, especially those fish that think they're food. Okay, anyway. Whoa, we really got off on that, didn't we? I did. Okay, so passive applications. Active application, solar collectors use to heat water. There is no reason, and we don't do it ourselves, I wish we did, but there is really no excuse for every house, in the South especially, not to have their hot water heater on the roof, in the south-facing roof. Because all it takes is paint it black, have the metal there. Now you have penetration in the roof that could leak, but you can seal those things pretty well. You ought to be doing most of the water heating through direct sun. There is really no excuse we don't do it, except it probably doesn't look good, or it may leak or something like this. But guess what? That is the easiest way, and that's one of the biggest hogs of energy in our house is heating water. And we can get the sun to heat most of them. Sure, at night it wouldn't heat, and in the winter it wouldn't heat much, but every bit that we could was to heat water, air, or some other liquid. So that is a really direct way that we could save tons of energy. Now, if you heat it hot enough, you can actually use it to generate electricity, but I doubt if many do. I think I've mentioned this before because I believe I asked the three guys back here. What does it mean to use regenerative braking? Y'all know that?
Like friction.
Yeah.
Causes deep heat and like recharge.
Okay. That's our standard brakes. The friction produces heat and the heat's blown away. That's what traditional braking does. Brake drum, brake pads, all that kind of stuff.
Regenerative heat, it goes back to your batteries that feed it.
Exactly. What you're doing, because it takes resistance to turn a generator, right? So you use your brakes to turn a generator with a strong magnetic potential in it, and turns it, produces electricity and goes back, like you said, into the battery. That's they use on hybrid cars, right?
You know what else is similar to that?
What's that?
The diesel engine.
The what?
The diesel engine.
Okay.
Cummins, J. Cummins.
Oh yeah.
That's what he did.
Okay. Do they do that in those
So
two?
the J brake, it regenerates the energy back into the engine to slow it down, slow the motor down.
Okay. All right. Good deal. All these kinds of things are things we need to be looking into, doing more. And I'm glad those kinds of things have happened. They need to keep happening. Big time. Okay? All right. Let's move on. More. You may not think of them this way, but a lot of wind energy is solar energy. Now, some of it isn't. Okay? But most of the times when you have winds, that's because you have columns of air moving up and air rushing in underneath it. That's a form of solar energy, is wind energy. And the winds, those turbines generate electricity. The wind is often inconsistent, but there's some areas of the country where wind blows and blows and blows. Chicago, the windy city. If you've ever been to San Francisco, I was stationed in the Navy for 3 years near San Francisco. I never was in San Francisco when it wasn't windy. It's off the ocean, and it just wind's always coming in there, and they have on the West Coast lots of these wind farms all up and down. We saw in Montana, in Idaho, they have the wind just comes whipping down the plains, okay? That was Oklahoma, right? Use it, okay? And yet people resist it, okay? So wind energy, I don't know why it does this. Okay, wind energy, some of that comes from the sun. The movement of heating of air and moving in behind it. But some wind energy is just basically from the spin of the earth. Because the atmosphere sort of stays in place, the earth spins around it. That makes it feel like wind here. So not all of this is from solar, but we'll give it credit for it. Okay? Biomass, that's what you were talking about. Okay? When you produce oil from your soybeans, your corn, actually, I know Alabama has a lot of this too, but Georgia, what was one of its more famous products, especially a few presidents? Say again? Peanuts, exactly. And when I was at the University of Georgia doing my master's, they had one of their buses that ran not on diesel, well, it was sort of like diesel, but it was peanut oil. And that was the best smelling bus when it drove by. Okay? It didn't stink like diesel, it smelled like peanut butter. Okay.
When you was in the military, did y'all run any Hercules motors, multi-fuel?
Now what's that?
Hercules motors?
Yeah, but when I was what?
In the military?
Yeah.
They offered like a vehicle that ran off of multi-fuel.
Mm-hmm.
And it ran like off of 18 different, like whatever you put in the different off.
Yeah. I've heard of them, but I wasn't directly involved with any of them. I heard of that a lot, yes.
I was gonna say, Max buses, UAB came up with something. Some of the Max buses run off like water or something like that.
Oh, really? Okay. So I
Well,
think,
the byproduct is the waste is water.
yes,
And this is hydrogen.
it may have been the hydrogen thing, the same thing they were looking at every year. Yeah.
UAB got invented or whatever, and then
Right.
Max bus was using them on the streets. I guess they still do.
Fantastic. It's good to hear we're doing those kinds of things. That's exactly what they talk about. See, biomass, the plant material, is formed by photosynthesis, those little green leaves catching the light, burned directly or converted to other fuels like the oils and the other things. The more we can do that and avoid the fossil fuels, we pick up all the sulfur and other things like that. Of course, there's some sulfur in peanut oil and others, but some of them have less than others. Now, some of this is really a little bizarre. Agricultural and industrial heating, the direct use of sunlight to do things like dry grain, cure paint, stuff like this. I just can't imagine we don't do that, except we're in such a big hurry to have things done immediately. We want to put it in an oven rather than let it cure naturally. I don't know. They talk about ocean thermal energy conversion. Now this to me I don't see, but maybe there is, using temperature difference between the surface and ocean depth to generate electricity. That seems like such a far-flung thing. But if they can do it, more power to them. Seems like to me we ought to have, in those areas that have high tidal surges, we ought to have generators turning when the tide comes in and generators turning when the tide goes out. Why aren't we using that? I don't know. Maybe they are somewhere. But seems like there's a lot of things that we could be using in such ways as this. Geothermal energy. Now, some of these percentages are a little bizarre. Okay, hot, dry rock, like I was talking about in Iceland, maybe in Yellowstone. I know in the Pacific Northwest, Battelle, I think is an energy company out there, that they have volcanic mountains around there. They use hot, dry rock. And of the geothermal energy, 85% of it comes from hot, dry rock. It's not 85% of energy comes from there. It's 85% of this geothermal, which is a very small slice of the pie. Hopefully we can make it increase. But this is associated with volcanic activity. Get close enough to a volcano, drill down. How they've had a few times when they drilled down, and the process of drilling down created a fissure, and they almost created an unexpected volcano activity. They don't want to do that, so they have to be pretty careful with it. But if they are, they can get down into that hot, dry rock, extract the heat with water, and then use that hot water for heating or possibly making steam and producing electricity. Then there's geopressurized resources. This is underground reservoirs of hot water containing natural gas. Now, which are they using, the natural gas or the hot water or both? I don't know. But they say about 14%. So this adds up to 99% are of these available resources. The dry steam, very, very rare, only 3 sites in the U.S., and I don't even know where they are. I'm guessing one of them may be in the Pacific Northwest, but I don't know that. One of them may be in Hawaii. I don't know that either. I don't think that Yellowstone has it, but possibly. Okay? But that's probably most of the other 1%. The hot water makes up most of the recoverable geothermal resources. It can be circulated directly into homes, like I said they do in Iceland, businesses, farms, and so on. But you have to be near a source of hot water. Now, there are those places that exist. Have you ever heard of Warm Springs, Georgia? Warm Springs, Georgia. You're from a later generation. Franklin D. Roosevelt was our president who had polio. And one of the places he would go, any chance he could to sort of get some relief, was Warm Springs, Georgia. And they actually had a place there. So that's just a place where there's warm springs. And how well you can capture that and use it, I don't know. Okay?
Cold Springs, Georgia.
Yeah. No, that's somewhere else, I think. Okay. But when we went through Canada one summer, or went through parts of Canada, my wife's family did a vacation up there, we went through Banff Springs, hot water springs, way up north in Canada, and always do that. And of course, Yellowstone. Those buffalo know exactly where to go in the dead of winter to stand in pretty warm water. Okay, so wherever you have geysers and activities like that, you know there's warm water somewhere in the area. Okay, it's just that we don't have that very frequently. Okay, but we got to use it when we got it. And then let's get to hydrogen. Here's the issue. The energy storage and transport system, you have to generate the hydrogen to use it. And it takes just about as much energy to generate it as you get out of it when you burn it. Okay? Now they say one possible source is water, and that's what they tried to use maybe in the MAX buses or maybe in over there, whoever was doing the renewable fuels over there. Anytime that you electrolyze water, you form hydrogen and oxygen. Okay? And then you can burn those two, turn around and burn them, and produce energy. But guess what? It takes as much energy to separate them as you get when you burn them. In fact, you always lose energy. Nothing is perfectly efficient. So the net result is going to be negative. Okay? So, but it's clean because the byproduct is water. Combustion produces water. Okay? Possible problems. I mentioned these earlier. Best stored as a liquid, but in order to liquefy hydrogen, you have to produce such incredibly cold temperatures. There goes all your energy producing the cold temperatures just so you can store the hydrogen. And then when you burn it, you don't get as much back out. Well, you could get a little more than you spent, but it's not a very productive process. The other issue is extremely flammable, just like the Flint people found out. So you have to be very careful how you store it. It escapes so easily because it's such a small molecule. And you have to store it under pressure, which means any break in the thing, you could have a big explosion in no time. So there are problems with it, but they probably aren't insurmountable problems. Okay? They give the illustration in the book to burn hydrogen with oxygen, you produce water, and it produces 68,300 calories of heat. That's a lot, okay? But in order to extract hydrogen from water, it takes 68,300 calories to get the hydrogen out of water. So it's almost a losing proposition. So they're coming up with ways to do it better, okay? In fact, maybe using other things to separate the hydrogen little bits at a time and then use it immediately. So you don't have the loss, and if your separation process is using something that's already there, not other energy. Just as an example, I think I used this one before. They talked about clothing with nanoparticles in them. So when you move and do this kind of stuff, you're producing little amounts of electricity. Because you're using energy. So anytime you have motion, that's energy. So use that to convert to that. Then use that, which you already have somewhere else, to extract your hydrogen in very small amounts, and then immediately use it in a hydrogen cell or something like that. It's sort of far out there, but possibilities. That's what we're looking for, possibilities. We've got to come up with something. We can't use fossil fuels forever. And that, by the way, is the end of the chapter. Okay, this chapter, and as I always say at the end of every chapter, and sometimes in the middle, nothing replaces reading the chapter. So please read the chapters. And when you do, the summary here is one of the shorter summaries I've seen. So, but read it. Notice the italicized words. Those are some of the more important words and terms. Then the summary of equations, 5 equations. The last chapter had like 14 or so. This has 5, but it's more than the first chapter. So these are pretty important. And most of these can be combined into other equations. For instance, work equals force times the distance. Remember that one? Well, force equals work divided by distance. Or distance equals work divided by force. Okay? So and power is equal watts divided by time, or work divided by time. So work is equal power times time. Time is equal to work divided by power. So every one of these can be converted to other equations. Most of them can. The key terms, again, a very short list, but know these. They give them alphabetical, but they list the page number where they're first defined or described. And then applying the concepts, which I think are the best study tools that you have in the book. There are only 36 questions here. Most of them are closer to 50. So this is, again, one of the shorter lists. But there's lots in those. I would definitely study the applying the concepts, multiple choice questions. Questions for thought, 12. That's maybe a little bit fewer than normal. For further analysis, this is one of the larger groups, 9 here. Usually only like 4 or 5. So again, all these are good to look at, and if you can work through some of the parallel exercises, unfortunately I don't think the little books have the answers like I requested, but if you have any questions about those, I'll be glad to try to work some of those. So how are we doing on time? We've been at it for what, about 2 hours now? Does anyone need a break? We're going to be going till 5:45, so only about 35 more minutes before we have lab. You need a break now or want to wait till lab time? Let me know. Second? Lab? Okay, we'll wait till lab time.
No, now.
Oh, now. Okay, I can't hear well. All right. Why don't you take a break? I'll get set up for chapter 4. Any questions on chapter 3 before you go? Okay, try to be back in less than 5 if you can. Okay. I think their program over there was called alternative fuels, not renewable fuels, or whatever. Oh, let me pause this. All right, I won't say all that again. But heat and temperature, you're talking about energy in many ways here, and this is a great thing to follow chapter 3 with. Core concept here, which you find on my book, it's page 87, whatever it is on yours. Core concept, a relationship exists between heat, temperature, and the motion and position of molecules. That's a really nebulous, broad-ranging statement. Doesn't tell you what the relationship is, it just says it exists. Heat and temperature are the same thing? No. They're similar, they're related, but they're like third cousin twice removed or something. They're not the same thing. Motion and position of particles, this again, more related to heat probably than it is temperature, but it's definitely related to temperature as well. Okay? Here's the overview. All right? Kind of how they break down the chapter. Okay? Most of the chapter is going to be talking about what the concept I brought up the word before when I was talking about William Thompson, when I was talking about James Prescott Joule. William Thompson considered to be sort of the father of thermodynamics. Now, what we mean by this, thermo means heat, dynamics means moving, changing, active exchange of heat, thermodynamics. Now, what we're going to be doing here, thermodynamics is the study of macroscopic processes, what we see and sense in the real world, involving heat, mechanical, and other forms of energy. Okay? That's the macro process. That's thermodynamics. Applications of this are systems with energy inputs and outputs, and for instance, heat engines. Those are your internal combustion engines, or heat engines. You put in a source of energy, a potential energy, fuel, and you produce heat, which produces the motion. Okay? Heat engines. Heat pumps. In this case, you're putting in electrical energy, and through a series of processes, you're producing heat. The reverse of that is refrigeration. You put in electrical energy, you produce the heat, you allow the heat to expand the gas, and then you let that gas contract again. That absorbs heat. That's your refrigeration and AC processes. Okay? Now, all these, the macroscopic things here that we're talking about here, are based upon, but not concerned with the microscopic details. The microscopic details are what's making all this happen, but you're concerned with the bigger picture, the macroscopic. Now, approach here that we're going to do is discuss first the microscopic processes, the underlying things, and relate those microscopic to macroscopic, and then get back to the concept of thermodynamics. So, this is how we usually think of things, but we're going to start this way and work our way back to that. So this is rather bizarre how they set up this overview. Boy, my throat hurts. All right, so let's start with, and this, I don't know why they did this. It's the one chapter that has dark background with white or light colored print. Every other one has been white background with dark print. They just switched them this time. We'll go back to the other next time. We're going to start with kinetic molecular theory. Okay. Again, this is a theory, but when they say molecular, what are you thinking? Molecules, incredibly tiny particles you can't see, you can't sense, but they're there. What do we mean by kinetic? Moving, exactly. So this is the movement of molecules and how that underlies everything that we're doing with heat and temperature. So the collective hypotheses, this is a whole group of hypotheses here, about the particular nature of matter. Matter is made up of these particles called atoms or molecules, and the surrounding space around those atoms or molecules, okay? And surrounding matter as well. Now, I think we've gone back to the Greek several times here. We're going to do it again and mention this. The Greeks were the earliest ideas written about the nature of atoms. Now, this is way before an atom, way before an atom could ever be really conceived, thought, or studied. But the Greeks thought through it and said, and the guy named Democritus, I think I've used this illustration before, he said, what if you had a piece of iron and you cut it into two? And then take the smaller piece of iron, cut it into two. Take the smaller piece there, cut it into two. And then keep doing, keep going. He said, how long could you do this before you finally get to the smallest particle you can have and it still be iron? So he called that smallest particle that it would. He just thought through this. He couldn't do it, but he just thought through it. He said that smallest particle, because it's indivisible, you can't divide it any further. The Greek word for that was our word atom comes from that. Indivisible. Nowadays we know you can divide atoms, but atoms are made up of smaller particles. But to be iron still, that's the smallest you could get, or any other material as well. So that was the early Greek view. The current view: matter is composed of microscopic particles. We call them atoms after Democritus. And these atoms combine to form molecules. Sometimes they're the same atoms, most of the time they're different atoms. Like two oxygens combine to form O2, two nitrogens combine to be N2, two hydrogens to be H2. Only one helium doesn't combine with anything, even itself. Okay? That's to form a single material, or you have hydrogen and oxygen combining to form water, H2O. That's a molecule of that. Nitrogen and hydrogen, ammonia, carbon and oxygen, carbon dioxide. They go on and on and on. Almost seems like an infinite possibilities. Okay? Many of the macroscopic, the big phenomena, can be traced through the interactions down on the atom and molecular levels. In fact, I would say most, not just many. Many of the macroscopic phenomena can be traced down to the microscopic level. So let's look at this concept called molecules, because it's kinetic molecular theory. Okay, so let's look at the molecules. Let's start simpler than molecules. Elements. Chemical elements are defined by each unique type of atom. Here's where you find all the atoms we know about today, and a few we don't know about. They're unknown, and they're listed that way. But the periodic table, that lists them all. All the ones we have any knowledge of so far. Some of these are missing. And you see UUS and UU or UNO, they've just made up some names here because they're not sure if they exist or what they are if they do exist. Okay. Some tables will leave those blank. This one actually fills something in. There's a UUP, a UUT, unknown, but they think there's something in there. somewhere, it's going to form one of those. Those are your atoms. The individual atoms, that's the number of them we have, they make the same material out of, the material's made out of the same type of atom, that's called the chemical element. Okay? So, while we're on this, let's think of it in terms of macroscopic, microscopic. The macroscopic term is elements. Iron, oxygen, nitrogen, whatever. That is the microscopic atom. Each one of those things I named has all the same kind of atoms. Oxygen atoms, nitrogen atoms, iron atoms, they're all the same. Macroscopic scale, they're the elements. Microscopic, they're the individual atoms. Okay. Then what are compounds? Compounds are pure materials, but they're made up of two or more different atoms. Chemically bonded. Okay? So they're totally different. Now here's the key. I think I've used this example before, but if not, I'll give it to you now. If I ask you what sodium is? Yes? What was sodium?
Salt.
Oh, no? Okay. What is sodium? Anyone know? Sodium is classified a metal, but it's not like metal you've ever seen it anywhere before. Chemically, it acts like a metal. Okay? Now, in its native form, it's yellow, but you don't see much. You'll never run across any sodium just out there lying around. Okay? And one of the reasons is sodium is so highly reactive. I'll just give you a clue on this periodic table here. Remember I said how active hydrogen was? Right under that is lithium, right under that is sodium. Everything in this first column is really, really, really reactive. It doesn't hang around as itself. It almost always combines with something else. Okay? So sodium is a yellow, very soft metal. But the reason you'll hopefully never touch any sodium, it would burn you like crazy. It's so reactive. If sodium gets in contact with just the least amount of moisture, water, it explodes. It's that reactive. So if you ever see sodium in a chemistry lab, it's going to be in a bottle stored under oil. So no water can get to it. Because if water ever got to it, it explodes. A lot like that hydrogen did in the blend. Except it didn't have to have a spark, lightning, or friction. It'll just explode on contact. So if you ever had any pure sodium touch you, you've got to burn it. Because it's going to immediately extract all the moisture it can out of you in a very hot manner. Okay, it's an exothermic reaction. It produces a lot of heat. So there's a hot, highly reactive, explosive metal, sodium. Anyone know what chlorine is?
It's a cleaning chemical.
Okay, that's Clorox. Okay, it has chlorine in it. You're absolutely right. But again, chlorine, very reactive. Okay, extraordinarily reactive. Chlorine's over here in the seventh column. The seventh column is just as reactive as the first column. There's fluorine, then chlorine, then bromine, then iodine, then blah, blah, blah. Okay? You might say, well, isn't the eighth column, wouldn't that be even more reactive? No. The eighth column in your periodic table has a filled shell of electrons. The outer shell has every electron in it it can hold. If it doesn't want any more, it won't react with anything. Helium, neon, argon, krypton, xenon, those are your noble gases. They don't react with anything. That's why they quit putting hydrogen in blimps, which would react with immediately. With helium, doesn't react with anything. And it's almost as lightweight, but not quite. Okay? So what is chlorine? Pure chlorine, not combined to make a cleaning product, but pure chlorine.
Yes.
It's a gas. It's a gas, exactly. It's a green gas. It's a green poisonous gas. Okay? You'll sometimes see the rail cars and they'll have chlorine on them. If those ever derail, clear the area because it's poisonous. It'll kill people, animals, everything. It's a poisonous gas. So here we take this highly reactive metal that will explode on contact with water with this poisonous gas, sodium and chlorine. And what do we make out of it?
Table salt.
Table salt, sodium chloride. And we put that on our food and eat it. You're probably eating some right now, aren't you? You're eating a explosive metal with a poisonous gas? Are you crazy? No. Because what a compound is a pure substance made up of two or more atoms, sodium chloride for instance, chlorine for instance, that are chemically bonded. That chemically bonding, that changes everything. All the characteristics change. It's no longer yellow, it's no longer green. It's no longer a metal, it's no longer a gas. It's a crystal salt. Okay? That is tasty and not very nutritious, but tasty. Okay? Makes food taste good. It also preserves food. It's necessary for our body. It's necessary. In fact, that's why we work. Because we are made up of chloride, of sodium ions and potassium ions that are a little potential difference from each other. That's what sends all the neuron cells, all the messages through our body. Sight, vision, hearing, everything, okay, is sent by sodium ions. Not sodium atoms, sodium ions. Okay, sodium compounds, like salt. So that's what it changes everything. The chemical bonding changes what they were into something totally, that's why it says a pure substance. Totally new substance has totally new characteristics. Nitrogen, the most common gas in our atmosphere, close to 80% of the atmosphere is nitrogen gas. Okay? Combine that with hydrogen, which is that very explosive gas, and you get ammonia that you use for cleaning stuff. Okay? Okay? It's just all over the place, folks. Every compound is a totally new material that has totally different characteristics from the atoms that made it up. Compound, macroscopic. Microscopic, these compounds made up of two or more atoms that could be the same or different to form molecules. So the microscopic concept, because the compounds is molecule, the macroscopic compound term that goes with elements is atom. Okay? Okay, so molecules. Molecules are the smallest unit retaining the properties of a compound. Atoms are the smallest unit retaining the properties of an element. Molecule is the smallest unit retaining the properties of a compound. Okay? So the shorthand here is molecule stands for. Okay, now here's another thing that you do run into. Just like I said, chlorine, fluorine, oxygen, hydrogen, nitrogen, all those gases, elemental gases, are made up of molecules of two atoms, O2, N2, H2, Cl2, F2. They're all made up. So a molecule can be an element, okay, but all the atoms are the same. But if a molecule has different elements, that makes a compound. So the shorthand here, molecules can stand for either atoms or bigger things like molecules. Okay, for instance, iron. An iron atom is the smallest unit you can have is iron. Rust, iron oxide, Fe2O3, smallest unit you can have that is rust, or it's called ferric oxide, rust. Okay, so an atom, a molecule could be a single atom, it could be two atoms, it could be a whole bunch of atoms, chemically bonded. Now, what are some of the molecular interactions we have? Usually molecular interactions are attractive. They're pulling things toward each other, causing materials to cling together. Okay? Now, that's the whole thing about the bonding, bringing things together. Now, one of these bonding type things is called cohesion. That's attractive forces between like molecules. Remember the lab that y'all were pouring water into the plastic containers, okay? And a couple of you, maybe not all the groups, because some of you were ahead of me, I couldn't see everybody at once, said, well, can't you add a little bit more? Can't you add a little bit more? And sure enough, if you keep putting water into a thing, and we'll see this, y'all saw it in the previous lab when we did the density. You can pour water into a container until you see the water explode at the top of the container. You'll actually see a mound of water there and nothing leaking out. It's because water molecules cohere to each other. They hang on so tightly that they keep them from falling off. Okay? Now, any of you ever jumped into a swimming pool and done what they call a belly flop? That hurts. Big time. Because water molecules are hanging on to each other so tightly, they don't want your body coming through. It feels like you hit concrete, okay? Not quite as bad as concrete, but it hurts, okay? Some of these high divers that dive off the really tall boards and stuff, quite often they don't have jam fingers, and things. They can really do some damage. And if they get out of line, boy, they can flip and really damage feet, legs, joints. It can be pretty bad. Water has cohesion, and lots of materials do. There's a second of these bonding interactions we call adhesion. That's the attractive forces between unlike molecules. Okay? When I go to wash my hands, the water sticks to my hands. I have to work to dry them off because water bonds to my skin pretty carefully. Unless, of course, I have grease on my hand. And then you wash and wash and you can't get the grease off your hand until you use a surfactant, which soap that will then help separate those, like a detergent. Okay? So the water wetting skin, that's adhesion. Water, one substance sticking to another substance. Most of your glue mechanisms, that's why we call them adhesives, right? Adhesive tape that sticks to you. Boy, it doesn't ever stick to you, okay? Now, there are some interactions that can also be repulsive, and that was water and oil. Water and oil do not interact at all, okay? They actually dislike each other. So when you wax your car, the reason you do that is so water doesn't wet the metal, it beads up on the metal and runs off. Okay? So your car remains shiny and good looking for longer periods of time. Okay? What causes these differences? The chemical bonding. Okay, you can almost bank on it every time. Let's go back to the attractive forces between water. Why does water do that? Will someone give me the formula for water again? Now, to write on these dark screens, I used to have to use a light pen, so I'm going to use yellow. What is the molecular structure of water? H2O. Now, how are those put together? Do you have an H here, an O here, and an H here? No. Okay? Now, when you get back...
543.
Oh, really? Man, how time flies when you're having fun. Okay. Let me just hit this real quickly if we can. Remember that last column that don't combine with anything because it's column 8? That means there's 8 electrons in the outer shell. Now, electrons always like to go in pairs. So that means there's 4 pairs of 2 electrons. They don't combine with anything else because they're happy just to be there. 7 is missing an electron, so it wants to react with something. The first column only has one electron. It wants to react with something, okay? So the 8, that's the key. Well, oxygen has potentially 4 pairs of electrons. But oxygen is only element 6. Well, no, it's element 8. But its outer shell only has 6 electrons. That's what I meant to say. It has a pair here, and then 2 singles. Okay? Now, to form 4 pairs around the central nucleus, the best way to do that is 1, 2, 3, 4. Any way you lay it is an equilateral triangle, right? Well, those pairs are like this. 2 of those pairs that are pairs, they're always adjacent to each other, and the other 2 that are singles are always adjacent to each other too. So, water forms like this. It forms an oxygen and then a hydrogen here and a hydrogen there. Now the hydrogen, okay, and then it has 2 other pairs of electrons around the now it's not flat like this. One's on top, one's on, it's in that tetrahedral structure. But what I'm getting at here, this is a shared electron pair. That's what a chemical bond is between that one electron around hydrogen and that one of those single oxygens. One hydrogen with one of the single oxygens. So this pair stays in here most of the time, leaving this hydrogen out here with a plus and a plus, because the electron is mostly in between the oxygen and the hydrogen. Whereas these extra electrons out here are on this end, that makes that a negative. Well, then the next water molecule that comes along, the hydrogen tends to relate to this, and the oxygen is sitting over here, okay? And the next one here, the hydrogen is here, and the oxygen somewhere over, oxygen here with another hydrogen there, say, okay? Over here, the oxygen's combined with a hydrogen sticking out here. Oxygen here with a hydrogen sticking out here. So what you have is electrostatic attraction. So these water molecules hang on to each other for dear life because they're attracted electrostatically. The minus from here attracted to the plus from there. The minus, yeah. Okay. Yeah.
That's why you see like the Olympics, you see them swimming, their head can come above the water before the water breaks.
Yeah, okay. I see slow motion when something coming up. Yeah, the water is hanging on for dear life, forcing the water out here. That's a very good example of this. Okay. Now, guess what? Water ought to be a gas. It should not be a liquid. Any other molecule that's as light as 18, and oxygen is a molecular weight of 16, hydrogen is 1 each, so that's 18. Every other substance that's as light as 18 is a gas. Water is the only one not. Why? Because of this, they call it hydrogen bonding here. That's holding them together so it forms a liquid at normal temperatures. Thank goodness. If it weren't for that, we'd have no life on the planet. So thank you, hydrogen bond. You enable us to live. All right, where are we going to go after this? Oh, phases of matter. That's right where we ended last time. So let's end it here. I think we used up all our time. Okay, we're now doing lab 5, which is the lab on energy. The last lab dealt with energy too. Is everybody in? Come on, everybody has to get in the room. Because we need to split into 2 teams. One team on this device and one team on this device. We got about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. Missing 3, yeah, that's right. So 5 and 5. All right, I guess we're split. That's good. Okay. Now, each side you'll see there's 2 meter sticks. I would use the wooden one, not the other one. Okay. Now, first thing you're going to do, Roman numeral 1 is from a previous life, different book, different everything. So, Roman numeral 2 is where we're starting. Experiments dealing with energy, and we're dealing with a pendulum, which these represent pendula. Okay. Now, here on the bottom here, we have 500 gram mass. Record that mass in kilograms. What is 500 grams as kilograms? Again, 500 grams. How many kilograms is that? How much? 0.5. Okay, 0.5 kilograms. So record that. Pretty hard, huh? 0.5 kilograms. Now, get one of your wooden meter sticks. Oh yeah, hey! Come on in. Did you go out to the classroom?
Yeah.
You did, okay. You saw the sign?
Yeah.
Okay, good. Let me get you marked here before I forget to. Come on in. Okay. Now, get one of the wooden meter sticks with the 0 in toward the floor, measure it to the base, the bottom, the flat bottom of that mass. Okay? In the meter end. Okay. I picked up a piece of paper and then I set it back down. What did I do with it? Okay, we've answered question 1. Roman numeral 2, question 1. Attach a 500 gram mass to the cord of the pendulum. Record the mass in kilograms. Did you get that already?
Yeah.
Okay, good. So with the meter stick, determine and record the minimum distance of the mass from the floor. With 0 in on the floor. Okay, turn it around with the meter side. Yeah. And do it to the closest tenth of a centimeter, but I want you to record that in meters.
Yeah.
23 centimeters. How much of a meter is that? Which is 0.23. Okay, what did you get? All these there. Huh? 42. 42, okay. And how many meters is that? That's centimeters. How many meters is that? 0.42. 0.42 for you. Meters. Okay. Now, one more meter stick here. Now, what we're going to do next is keeping the string taut or tight. Okay. Put it on top of the meter stick. Okay. And the next fourth. Okay. How high is it above the floor now?
1 meter.
1 meter. Okay. So what was the change of height from down there to up here? It'll be different for you from you.
58.
Yeah, exactly. From 1.
Well, over
5.8 meters.
5.8 for you, right? What was yours before? Yeah, 0.2 something. Yeah. Okay. All right. Now, everybody got number 3 done. Okay, number 4. My question for you is, what is the gravitational potential energy sitting here on top of this meter stick?
0.
Gravitational potential.
Oh, gravitation.
Yeah, gravitational potential energy. What is the formula for gravitational potential energy? mgh. And this h is going to be our delta h from the previous question. So what's its mass? 0.5. What's g? 9.8 meters per second squared. And what's the delta H? That's for each of you to answer because you just filled it in, right? So anyone brought a calculator? Okay.
Frankie's got one right here.
The GPE at the top. 9.8 is G.
9.0.
Did you get your gravitational potential in 2.8? Right. And what did y'all get? Okay. Sound reasonable. Okay. Now, that's GP at the top. What's the volt?
What are the units for that?
Oh, good question. I left that off, didn't I? Well, the mass is in kilograms. The acceleration due to gravity is meters per second squared. So a kilogram meter per second squared would be a Newton. And then multiply that by a meter. A Newton meter is a joule. Exactly. J, capital J. Named after James Prescott, who we looked at today. Okay, next question on number 4 is what's the velocity at the top? That's 0. It's not moving, is it? Okay. Velocity at the top is 0. What would be kinetic energy at the top? Why? It's not moving. 1/2 mv squared. If velocity is 0, kinetic energy is 0. What is the mechanical energy at the top? What is mechanical energy? What's the definition of that? Ooh. Mechanical energy. No one brought a book in, did you? Okay. It's the sum of the potential plus kinetic. Yeah, whatever yours is.
The potential and kinetic.
Yeah.
And is it still in joules?
Second, still in joules.
Okay.
Exactly. Now, I'm going to release this mass, and you could do the same thing over there, except it might hit me, so I don't want you to. Okay, but it'll do the same thing. I'm going to release it from the top, okay, and not throw it, but release it. Ooh, I knew it. And there it did that. So you can pick that one up and put it up there with those up. Yeah, over there. This thing has been abused so much. Let's see if I can do it without it hitting it. We'll see. All right. Where is its maximum speed, you think?
Coming back.
Okay, coming down, but where does it reach its max? At the very bottom. Did any of you measure the speed while it was down there? No, that was very tough to do because it's always changing. Okay? So here's what we're going to do. What do you reckon the mechanical energy at the bottom was when it was swinging like that? Mechanical energy at the bottom. Say again? Yes, it's exactly what it was at the top because mechanical energy is conserved. It doesn't change. What's the GPE at the bottom when it was swinging? It's what?
It's still the same.
Really? GPE up here was one thing. Down there it would be, it's lost gravitational potential energy, hasn't it? So, what do we call that? Oh, I should have said this. That when we did the meter stick, number 2, at the bottom, that was its 0 reference point. Did you see that in parentheses?
Yeah, I see it.
That means that H down there is 0. So, what would the gravitational potential energy be? 0. GPH would be 0. MGH would be 0. What would, okay. Number 5.
5 GPE, right?
Okay. Yeah, the mechanical energy at the bottom was whatever it was. Okay. Then the GP at the bottom was 0 because the H at the bottom is 0. That was your 0 reference level. Okay. The kinetic energy at the bottom would be what then?
2.8.
Yes, whatever your mechanical energy, because none of it's potential at the bottom. Now, with that in mind, we can calculate the velocity at the bottom. Because the velocity at the bottom is We know kinetic energy. And kinetic energy is what formula?
1/2 mv squared.
Perfect. So we got kinetic energy at the bottom, 1/2 mv squared. Let's solve for v. So multiply both sides by 2. So 2 times kinetic energy is equal to mv squared. Then divide by m, whatever that is, that's the 0.5. And that gives you v squared. And then how do you get v out of v squared? Take the square root. Okay? Another calculator.
You want it in decimal or fraction?
I'd rather have decimal, I think. 1.24.
Yes, sir.
Okay. What would that be in?
3.9. Should be in meters per second.
We're still in meters.
No.
Or we're not. I'd like to say,
Velocity.
meters per second.
Meters per second. Very good. What did y'all get?
3.9.
1.24
Okay.
meters.
3.9 meters per second.
Okay. Let me see a few of your calculations again. Let me see your 0.5 MGA.
So we're going our 2
Good.
point.
Okay, yeah, start over. Okay. Let me see the 0.5 times 9.8 times, and what was your delta H?
Delta H is
0.58. Yeah, that's what you got. Okay. All right. Now, let me see you do the next. First, you multiply by 2. Okay. And divide by your mass, which is 0.5. Okay. And then take the square root of that.
square root of square root.
No, that's not the square root. The square root is that one. Only the 2 in it.
And then that's a little bit of it.
And do the square root, which is that. Yeah, that's better.
3.3.
3.3.
Oh, he's here. Oh,
We're almost done.
All right,
With moving
good.
and everything.
Okay. Yeah, let me borrow it for a second.
Meters per second.
Oh, of course. Always happens. Okay. So all we're missing today is the treatment. Okay. Okay. And poor Ryan has to come to this group. All right. Oh, wait. Yeah, Ryan.
Well, he's copying from mine.
I know. Yeah. You need to get in this group. So you need to copy from this guy. Yeah. Sorry about that. So now y'all have 6, right? And y'all have 6. Okay. All right. So y'all got velocities. What units did you get?
Meters per second.
Meters per second. Excellent. Okay. Sorry about that. Now. Sorry. I hope I'm not contagious. Okay. Now we're going to do the next part, number 6. I need a person over on this side and a person over on that side manning a meter stick. Okay, you got to that side with that meter stick. Someone over here with this one. Okay, that side over there. Right? Sorry. Yeah. Okay, no, we're going to use this one. We could use either one, but that one hits on that so badly. Okay, get on over a little bit. Now, so when you pull this to the top, you have full range. Pull it to the top, keeping the string tight. Okay. Now we're going to do a couple preliminaries. I'll get down there. Oh no, we're just going to use this one. Yeah. Okay. I want you to measure, so you can stay far enough away so you can measure how high it comes over there. Okay. This time we're just going to release it. This is on your thing. want you to, you're leaving from a meter here, see about how high it gets here. Release it from rest.
Stick this land on the stick.
Okay? About how high did it go?
Same.
Almost to a meter. Okay? Don't record that. Okay. Whoa. Okay.
I got
Put this back on. Yeah. I can do it. Just hook that on the hook at the top. Okay. This time I'm going to peg it. Okay, put it back on the top. Okay. I'm going to peg it about a third of the way down. Does that look about right? You can bring your stick in a little bit. That's about right. That's good enough. I'm going to peg it here, and y'all see about how high it goes there.
Ready?
Yeah, anytime.
Almost in the center.
Almost to the top, so about a meter. That one you can write down. Number 6, approximately to what height does the mast go? 1 meter. Okay. Now,
So now we do halfway, Dave.
okay, I'm going to do it halfway now. So you put it on top again, get your meter stick set up, about halfway down. Okay? About right. Okay. I'm going to peg it about halfway down. How high does it go? About a meter. Okay?
Two-thirds of the way down.
Okay, I'll do that next. Okay, set it up. About here. Okay. All right,
You don't know.
set it up.
You can't
Okay.
get to the top, that's for sure.
What happened?
Wrapped around.
It wrapped around the peg. Uh-oh. So record that. Repeat the process with the core peg about 2/3 of the way down. 2 answers to this one. First, what happens to at this point? Y'all just saw what happened. Wrapped around the peg. Now the big question, this is the second part of this one, why?
The energy continued to carry
The
on.
energy kept. It kept on putting down.
Okay.
I'm trying to word it. I know.
I think you're right on track. Why did it stop the other 2 times?
Because you were higher up.
Okay, yeah, but where did it stop? But every time?
At the same distance.
At about a meter. Why did it stop there?
Had enough string to get to it.
Okay, you're getting right close to it because when it got over here, it only had enough mechanical energy to go to that gravitational potential energy. Stopped because kinetic energy went to 0, right? But when you went 2/3 of the way down, what did you not have? Enough string to get back to a meter. So if it couldn't get back to a meter, it couldn't lose all its kinetic energy. So it lose all its kinetic energy to get back to that gravitational potential. So it maintained some kinetic energy, which meant it went in a circle. Okay, good deal. Y'all are the quickest class to pick up on that of any class I've had.
So it maintained its kinetic energy.
It maintained some of its kinetic energy because the string was too short to get back to a meter. Absolutely right. That's the second part of 8. Now, when you finish writing, number 9. What conservation principle does this experiment demonstrate? Both parts of it. What was always conserved?
The
Mechanical energy. Kinetic was always changing, potential was always changing, but the mechanical energy was conserved. Okay. Let's go back to the classroom, this classroom right here, so you don't have to sit around the floors and write on various surfaces. Yeah, I'll take it.
What did you write?
down. Okay. All right. I'd like. Okay. All of you who are on the left out here, back there, you can call it whatever you want to. Your minimum displacement was 0.23, right? So all of you who are on the right, in the margin out here, right next to your 0.42, you write 0.23. And all those who are on the team over here, you write 0.42 for your number 2. Okay? And then you do your calculation. Don't get with the other team. Just redo the calculations that you just did to get all of your Okay, does anyone have any questions or need the lab still recording any longer? Everybody okay? All right. I'm going to shut